All right, welcome to this explainer. Today we're unlocking quantum computing. Now, I know a lot of people tend to picture a quantum computer as just, a supercharged, incredibly fast version of the laptop you're using right now. But honestly, we need to clear that up right off the bat. It's absolutely crucial to understand that they aren't just faster ordinary computers. They operate on a totally different set of rules for how information even exists. And that difference is exactly why the whole concept can feel so incredibly counterintuitive at first. To really wrap our heads around this, think about reading a book. If ordinary computing is like reading that book page by page, line by line, fact by fact, then quantum computing is more like letting the book influence all possible endings at the exact same time before you even crack it open to see which one becomes reality. Crazy, right? It's just a completely different way of interacting with information. Okay, let's dive right into this and look at the strange power of qubits. So let's look at the absolute fundamental building block here. In your everyday ordinary computer, information is stored as a normal bit. Think of it like a light switch on your wall. It's got a hidden label that says it's either firmly on or firmly off, a 0 or a 1. Simple. But a qubit, it absolutely does not behave like a tiny switch. Actually, scratch that. It's much more like a spinning coin before it lands. While that coin is spinning in the air, it isn't heads or tails yet, right? It's a physical, active object holding both possibilities in a very meaningful way. It's not just some secret answer hidden inside a box. It's an active condition carrying all those options until something physically forces it to stop. Which brings us to this absolutely beautiful quote from our source material. A qubit behaves more like a wave of possibility than a box holding two separate answers. I love that. Think about tossing a pebble into a pond. When two water waves overlap, sometimes their peaks add together and get massive. But sometimes a peak meets a valley and they just cancel each other out entirely. That wave-like behavior, that is the literal source of quantum computing's strange power. A qubit isn't just a giant pile of random guesses. It has a literal shape of possibilities that can interact, overlap, and, cancel each other out. Let's move on and see how this builds, focusing on how we actually shape these waves of possibility. Now that we've got a handle on what a single qubit is, we really need to understand how the actual machine calculates. So, in ordinary computing, the logic flows through exact fixed states. Input goes in, operations transform it, output comes out. Boom. Because it uses these fixed values, you can safely check in on things along the way. Peeking at your data halfway through a normal computation, totally fine. It doesn't destroy the data. But, as this brilliantly illustrates, quantum computing is a whole different ballgame. The operations here don't just flip zeros and ones, they reshape probability-like amplitudes. And here is the huge catch. Checking too early destroys the state. You absolutely cannot peek halfway through. The output can only be revealed at the very end. The machine is essentially managing this highly fragile living pattern of possibility. So you might be wondering, how on earth does it actually find the right answer if we can't peek? Well, it does it through something called interference. And listen, interference isn't just some weird side effect. It is the true engine of quantum computing. Imagine trying to navigate a giant maze. A normal computer is going to check every single path one by one. A quantum computer, though, it sets up a pattern of possibilities so that the wrong paths literally cancel each other out, while the right path is amplified and becomes super obvious. It doesn't use magic to guess. It literally forces the wrong answers to fight each other. If it helps, and I think this analogy is great, think of the computation like choreography. Imagine a massive dance floor filled with spinning dancers. A quantum algorithm is kind of like a choreographer who doesn't yell out, "Hey, which pose is correct right now?" but instead carefully adjusts how the dancers are aligned with one another. The real power of the performance comes from how they interact along the way, completely unseen before the music finally stops. Or let's try another vivid analogy. Imagine a flashlight in a foggy room. The qubits are essentially this foggy field of possible outcomes. The algorithm acts like setting up a bunch of specific light beams and mirrors. The value isn't in walking around and staring blindly at every single corner of the room. The value is in setting up the light perfectly so that the important structural shape just suddenly appears and becomes visible to you. Now, what's really interesting here is how this scales up. Let's talk about entanglement in the system as a whole. Because look, if one qubit is interesting, it's super tempting to think, oh, 100 qubits must be 100 times more interesting. But quantum systems absolutely do not scale like stacking paperclips. They scale through this wild phenomenon called entanglement. Let's go back to our dancers for a second. Imagine two dancers holding a single ribbon. If one dancer turns, the ribbon immediately pulls and affects the other. You can't fully describe what one dancer is doing without describing the other. Their behavior is totally shared. Once qubits become entangled, you can no longer treat them as these isolated little boxes. The entire system has to be viewed and mathematically described together as one completely linked whole. And honestly, this is exactly why quantum computing is not just parallel computing on steroids. Parallel computing, that's like having 10 independent cooks in a massive kitchen, each making a separate dish at the exact same time. Sure, it's a lot faster than one cook doing it all. But quantum computing is like one shared master recipe, where the ingredients are intricately mixed from the start. Every single step affects the next, and all the possibilities interact. The final flavor depends on the entire interconnected process. That deep interaction, that is exactly where the real quantum advantage lives.
So, this brings us to our final act, a totally new way of thinking about computation.
We've talked a lot about spinning coins, choreographing waves of possibility, linking them all together. But how do we actually get the final answer out of this delicate, intertwined system? Well, it all comes down to measurement. Measurement is the final, irreversible moment. In ordinary life, looking at a book on a table doesn't rewrite the story inside it. But with qubits, measurement is like opening a sealed envelope that holds a super delicate folded paper sculpture. The very act of opening it forces that sculpture into one visible, fixed shape. Or, think of it like taking a photograph of a fast-moving waterfall. After that exact moment, you no longer have a flowing wave of possibilities. All possibility just collapses into one definite outcome.
So the crucial point here is how this all loops together in a completely non-magical way. Step 1, your qubits hold a massive spread of possibilities. Step 2, your quantum operations carefully reshape those possibilities. Step 3, interference kicks in as the tool to strengthen the right paths and completely cancel out the wrong ones. And finally, step 4, measurement reveals the final single outcome. It is such an elegant system for guiding possibility directly toward a concrete result.
Which leaves us with a completely new paradigm. Look, quantum computers are not going to automatically be better at everything. If a task is already easy for your laptop, quantum mechanics doesn't magically make it better. So, the next time you hear about some massively complex logistical problem in the news, you don't need to wonder, hey, can a quantum computer just think faster to solve this? Instead, you should ask the exact question that a true quantum engineer asks. Can this problem be expressed in a way that interference gives us an advantage? Once you start asking how the underlying structure of a problem interacts with the structure of the machine, you've basically unlocked real quantum intuition. Thanks for joining me on this explainer. Remember, the future of computing isn't just faster, it's fundamentally entangled. See you next time.